Okay, so this is the start of lecture number 4, and we're going to spend a few more minutes on Lewis structures and resonance, and then move on to the next topic. So we had done an example of Lewis structures in class, and then I think one at the end of the last lecture. Let's look at a couple more. Let's try, for example, looking at cyanate, so CnO minus. So the question is going to be two parts. One is to build the most stable Lewis structure or structures of cyanate, draw the hybrid, and then comment on the appropriateness of the hybrid. So the three things. One is to build the most stable Lewis structures, and there's going to be an S here, so structures, because there may be more than one. 2, draw the hybrid, and then 3, comment on its suitability or something. In other words, does the hybrid represent a reasonable depiction of the species you're drawing? So the way we do this, and in a question like this, I will often, when there are multiple atoms, when it's triatomic or more, unless it's a species that's very common, I will tell you what the connectivity is. Because with C, N, and O, I mean, you don't know which one is central. So let's do the one where N is central. So I will probably tell you it's CNO. So the first thing I'll do is I'll write C to N to O. Right? So a Lewis structure gives the number and arrangement of all the atoms. Number and arrangement of all the atoms. But then it also gives the number and arrangement of all the valence electrons. So let's do that. Let's get the number of valence electrons is equal to 1 times 4 for the group 4 carbon, because the group number gives the number of valence electrons. That's how you define them, right? Plus 1 times 5 for the group 5 nitrogen, and there's only one of them, plus 1 times 6 for the group 6 oxygen, plus 1 for the negative charge. And that gives you a total of 9, 10, 16 valence electrons. Of those 16 valence electrons, we've already accounted for 2 of them in this sigma bond, and 2 of them in that sigma bond, those 2 bonds. So 4 of the 16 electrons are already accounted for in the inventory. There are 12 left. And so how do we get those 12? Or how do we apportion the 12? And the rule of thumb is you place the 12 electrons around the peripheral atoms first, making sure we don't exceed the noble gas configurations. And if there are any electrons left over, then you populate them around the central atom. And you'll learn this in Gen Chem. So I've got 12 electrons. I'm going to go, doesn't matter which one, 2, 4, 6, 8, 10, 12, and we have got no more. Okay, so that gives me the number and arrangement of my atoms. Number 2, 4, 6, 8, 10, 12, 14, 16, and an arrangement of my valence electrons. But a Lewis structure is also given the responsibility of identifying the formal charges. And again, how do you do formal charges? We count how many valence electrons a particular atom has and compare that number to the number it should have based upon which group in the periodic table it exists. If an atom has more valence electrons than it should have based upon its position in the group, then it's going to have a negative charge. If you've got more electrons than you should, you'll be negative. How negative? By the difference. Right? So if I have 2 electrons more than I should, I'll have a 2 minus charge. If the atom has fewer electrons than it should, based upon where it is in the periodic table, it's going to have a positive charge. right? If I'm missing electrons, I'll be positive. How positive? By the deficit. So if I'm missing 3 electrons, I'll have a charge of 3 plus. Now if the number of valence electrons that I have equals the number of valence electrons that I should have, so there's neither a surplus nor a deficit, then there'll be no charge. There'll be no negative charge for a surplus of electrons. There will be no positive charge for a deficit of electrons. So that's the game we're going to play, and we're going to do counting. So we've got, for the carbon, 2, 4, 6 that belong to carbon only, because those are lone pairs, right? They're non-bonded pairs that belong to the atom only. But in the covalent bond, one of these electrons is carbons, one is nitrogens. So the counting for carbon goes 2, 4, 6, and 1 in here is 7. It is a group 4 element. It's got 3 electrons too many, that's a 3 minus charge. What about the N? It's got 1 electron in this bond, 1 electron in that bond, that's 2. It's a group 5 element, which means it's got two electrons. Oh, sorry, it's got 2 valence electrons. It's a group 5 element, so you're missing 3 electrons, hence a 3 plus charge. I got lost there for a second. Now, without thinking too hard, if this is 3 minus, then that's 3 plus, so they cancel. It must be that the charge in the O must be 1 minus. Let's verify. 2, 4, 6, and 1 in here is 7. It is a group 6 element. It's got 1 electron too many, hence the negative charge. Okay, so I'm going to ask, is this the best structure for cyanide? And how do I know that? What parameters do I use to gauge the stability of a loose structure? If you remember, we look at the number of atoms with noble gas configurations. We look at the number of bonds, and we look at the degree or the extent of charge separation. Right? The more atoms with noble gas configurations, the more stable we are. The more bonds in the structure, the more stable we are. Bonding stabilizes. We look at that in a little while. And the fewer atoms that I have that are charged, and the lower those charges are, the more stable we are. Because nobody likes to be charged. So if I look at the modulus of the charge, right, as the lower that number is, the better. If I look at this structure, both the carbon and the O have noble gas configurations. That's a great thing. The nitrogen does not. So immediately this is not a good structure, right? It's not the most stable structure. It's a valid Lewis structure. It's just not the most stable one. Besides that, I've only got 2 bonds, and that's in a system where I've got a divalent atom, a trivalent atom, and a tetravalent atom. Surely I could muster more than 2 bonds. And then thirdly, I have separated out a 1 minus charge into a modulus, an absolute value of 7. So ignoring the signs, right? This is 3, 3, and 1. So that's pretty bad. And in fact, 2 of the atoms actually have pretty high charges. That's not good. Can I fix it? Absolutely. I'm going to move electrons in from the electron-rich site to the electron-poor site. My instinct would be to move it from the 3 minus towards the 3 plus, because there's a greater electron pressure here. Plus, and I'm going to preempt something here, of the 2 atoms, C and O, carbon is less electronegative. It is much less adept at supporting a negative charge. O is pretty electronegative. O doesn't terribly mind having electron density, but the carbon doesn't like it. So if I had a preference, I would want to rid the carbon of electron density. So I'm going to dump electrons from the carbon to the CN bond. I'm going to draw my resonance arrow, and that's going to give me C, double bond N, single bond O, which I have not touched. And I'll have 1, 2, 1, 2 valence electrons. It's a lone pairs. Formal charge of the carbon is going to be 2 minus. On the N is going to be 2 plus, and there'll still be a 1 minus charge in the O. Again, I'm just going to do this one more time because we've done it several times. I can get these charges in one of 2 ways. I can count. I can go 2, 4, 1 in here 5, 1 in here 6. It's a group 4 element. It's got 2 electrons too many, 2 minus charge. For the nitrogen, 1 in here, do a running count. 1 in here, that's 1. 1 in here, that's 2. 1 in here, that's 3. It's a group 5 element. It's missing 2 electrons, and therefore a 2 plus charge. And we didn't touch the O, so that's fine. I can do this another way. There is a 3 minus charge on the carbon when it owns both of these electrons. This action gives an electron to the end. So if I am 3 minus and I lose an electron, well, I'm going to be 2 minus. Right? So it's a 2 minus charge. So likewise, there's a 3 plus charge in the nitrogen in this current iteration. This action gives the end an electron. If I am 3 plus and I gain an electron, I'm going to be 2 plus. Is this a great structure? Well, it's not a great structure because the N still does not have an octet. Now, everybody else does, right? 2, 4, 6, 8, 2, 4, 6, 8. So the donation by the carbon doesn't hurt the carbon. Right? There's no skin of the carbon's nose to dump electrons towards the nitrogen because the carbon doesn't lose an octet. If anything, it's good for the carbon because we are getting away from a 3 minus charge. And the entire system gets more stable because the N is now closer to an octet and the charge is now smaller. Is it perfect? No. Can I fix it? Yes, I can give the N an octet if I take one of these lone pairs and dump it on the nitrogen, and that's going to give me this structure. So C, triple bond N, single bond O. And if I do that for any number of reasons, either by the counting or by looking at what happens to the charges, when I move the electron pair, I'll have a 1 minus on the carbon, I'll have a 1 plus on the N, and I'll have a minus charge below. And again, if you sum those, the overall charge here is going to be minus 1. Okay, now, can I stop here? Well, let's see. If I call this structure 1, and I call this 2, and I call this 3, clearly, if I were to rank those in terms of stability, I'm looking at these parameters to gauge stability. Then structure 3 has all of the atoms with noble gas configurations. 2, 4, 6, 8 for the carbon, for the nitrogen, 2, 4, 6, 8, for the oxygen, 2, 4, 6, 8. So they all have noble gas configurations. And now I have 4 bonds, that's the most that I've had in the structures. And my degree of charge separation is actually pretty small. My modulus is 3, my absolute value is 3, which is less than 5, which is much less than 7. So of the 3 structures on the board, this is the most stable. Okay, there is and I can ask myself, do I stop here? Well, there are 2 ways which I answer that question. If you remember, if we're looking at these structures, let's say particularly this structure 2, I could have brought electrons towards the end from either one of these 2 electron sites. Now I chose to move the electrons first from the carbon because I argued, well, carbon, the charge on the carbon is greater than on the O. Carbon doesn't like the negative charges, so it's the more desperate to get rid of them, so I made that argument. But in reality, I could have moved the electrons from the O towards the N. So when I look at the structures, that alerts me to the fact that there's a possibility of not just moving electrons this way, but also that way, which creates an entirely different resonance form. So with that in mind, that's argument 1, with that in mind, I can look at this structure and say, look, I can actually go ahead and do this, and if I do, I'm compelled to move that out. And that gives me another resonance form that looks like this. C double bond N, double bond O, 1, 2, 1, 2, and then 1, 2, 1, 2. Formal charge in the atoms. If I do this, the O will now have no charge, because it was minus 1, I'm going to donate an electron. The N, which was positive, gets an electron, and then loses an electron. So there's no net change. that is now going to be +1. The carbon, which was -1, is gaining an electron, hence that is now -2. And again, if I were to sum the charges, the formal charges, I'm still -1. Let's call this structure number 4. Okay. Now, so the question I asked is, when do I know when to stop? So one was the fact that I had a central plus and 2 peripheral minus charges with electrons. It means I could move electrons either way. And I had so far only moved from the carbon towards the end, but I know I can move now from the O towards the end as well. Okay, that's one. But the second reason why I know I can go further than this is because this system is in what we call the resonance condition. And the resonance condition occurs in the following cases. If I have, let's say it's X, Y, and Z. If I have a negative charge, which is a single bond away from a multiple bond, this can be double or triple, I can do resonance. And the resonance will go bang, bang, and we end up with this structure. So X double bond Y, Z minus. Now, you remember we talked about this in class, that I may give you a structure where I don't have lone pairs, where we don't know what the atom is, so we don't know whether they're lone pairs or whatever, how many lone pairs are around each atom. But I don't need that to know what the charge distribution is going to be. If I tell you there's a minus charge in this atom, and I move, and a minus charge is tantamount to a lone pair of electrons, right? We've seen that in all the examples. If I move this electron pair in, I will have to move this electron pair out. So what does that mean? This atom, in moving that pair of electrons in, has given away an electron. So its charge goes to 0. The Y, whatever it is gaining 1 electron from the X, but losing 1 electron to the Z. So whatever charge was on the Y stays. The Z is gaining an electron from the Y. So the charge in the Z becomes 1 greater, becomes a 1 minus greater. So in a system like this, I don't need to know who X, Y, and Z are. I don't need to look at how many lone pairs are around them. I can reason what happens in terms of the charge distribution. So whenever I have a single bond, whenever I have a negative charge, a single bond away from a multiple bond, whenever I have a negative charge, a single bond away from a multiple bond, double or triple, I am at the resonance condition. So I am compelled to do another resonance form. This is also true. This is also true. Well, I'm gonna. Well, so you guys can erase as necessary. This is also true. Yeah, I'll just do it here. This is also true if I have an X with a positive charge, a single bond away from a multiple bond. In which case, electrons flow from electron rich to electron poor. I will do this, and I'll have X, double bond Y, single bond Z with a plus charge. How do I know that? Well, what is happening? The Z is taking an electron pair and dumping it between X and Y. So the X is getting an electron it did not have. So it goes from 1 plus, if I gain an electron, I go 0. The Y has an electron in this bond. But that bond is going. It's okay, because now the bond is formed here. So the electron that Y invested in this bond is still here. So Y isn't losing anything, it's not gaining anything either. It's just transferring from here to here. So the charge on Y does not change. But Z invested an electron in the ZY bond. That electron now is gone away from the Z completely. So Z has lost an electron ultimately to X. Therefore, charge on Z becomes positive. And the third example, which I'll draw now, is if I have X with a lone electron attached to Y in a multiple bond to Z. In a case like that, one of these electrons goes here, one of these goes here, and the other one goes here. Now, as we get more mature in organic, I will simplify that diagram a lot more. But essentially what is happening is I will take this electron, pair it with one of these electrons to make an X-Y double bond, and Z is going to end up with one electron, right? And therefore what I end up doing is transferring the lone electron, or pair, lone electron onto the Z. You will notice something here in that the curved arrow that we use to depict electron motion is a full headed arrow when we're moving two electrons. But it is a partial arrow, it's called a fishhook, when we're moving a single electron. So the resonance condition arises in a very specific set of circumstances. If I have X a single bond away from a multiple bond, and X bears either a lone electron, a positive charge, or a negative charge, I am at the resonance condition. Resonance is going to happen. Now there's one more example we will do as the course matures, but these are the three that you'll have to mess with in the early part of the course. So I knew when I got here, there was another resonance form to draw. Okay, now, if I wanted to gauge the relative stabilities of the four resonance forms, and you have to go back and look at the ones that we had earlier, well, I can just write really fast here. So it's C, N, O, 2, 4, 6, 2, 4, 6. That's 3 minus, 3 plus, minus. And then we had C, double bond, N, single bond, O. 2, 1, 2. So this was 2 minus, 2 plus, and then that. Okay. And this was 3, this would have been 2, and this is 1. If I were to rank them, and I don't want what your gut feeling is, what your instinct is, none of that stuff, right? It's not voodoo. There are structured rules that we use to determine relative stability. So, number of atoms with noble gas configurations. Well, both structures 3 and 4, and only structures 3 and 4, have all 3 atoms with octets, right? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So, from that perspective, structures 3 and 4 are equivalent. Number of bonds, 4, 4. So from that perspective, structures 3 and 4 are equivalent. Degree of charge separation. Well, my modulus of charge, my absolute value, is 3. In this one, it's 3. So from all 3 measurable parameters, structures 3 and 4 are identical. So we would argue then that the hybrid is a composite, a weighted average of these 2. So let's draw the hybrid. The hybrid then, so when I want to build the hybrid, the question I have to ask myself is, what are the most stable resonance forms? Determined by these factors. When I have those resonance forms, those most stable resonance forms, and by the way, that can be one structure that's a clear winner, and we ignore all the others, in which case the hybrid is that structure, like in the case of cyanide. Sometimes it's 2 structures, sometimes it's 3, 4, 5, and so on. So we use the most stable structures based upon these parameters to construct the hybrid. So let's see what the hybrid looks like. So the hybrid is going to have C, N, O. How many bonds between the C and the N? Well, it's an average. The average of 3 and 2 is 2.5. Because 3 and 2 is 5. The average of that then is going to be 2.5. So there's going to be a bond order of 2.5. How many bonds are between the N and the O? Well, it's an average. The average of 1 and 3 is 1.5. So 1 here and a half. And it's customary to kind of show the dotted lines as a whole, long line, right? You put them together. It's customary. So the bond order here, so BO is bond order. That's 1.5. Okay. And that just shows now the bond orders. Again, if I sum the bond orders, 2.5 and 1.5 is 4, that should equal the number of bonds in any one of the major forms. So I'm double checking myself. There's an internal consistency. I also want to get the formal charges on the atoms. What is the average? What is the charge on the carbon? It is the average of these two. What is the average of 1? 1 plus 2 is 3. What is the average of these two numbers? 1.5. Right? So the average of 1 and 2 is going to be 1.5. Or put another way, if I add negative 1 and negative 2, and divide by 2, because they're two structures, that's negative 1.5. So the charge in this is minus 1.5. What's the charge on N? Well, what's the average here? Right? That's going to be 1 plus, right? If I add 1 plus and 1 plus, that's 2 plus, and divide by two structures, that's going to be 1 plus. Minus 1 and 0, and then divide by 2, that's minus a half. If I sum the charges, it must equal the charge on the actual species. So negative 1.5 and negative a half is negative 2. Negative 2 plus 1 is negative 1. And that's the structure I'm drawing, CNO minus. So question 1 was, build the most stable Lewis structures. Right? I started with a species, moved the electrons as appropriate. I ended up with these two structures that were the most stable, as measured by these parameters. Check 1. Draw the hybrid. I am going to ignore the others, which are not particularly stable, and use the two most stable ones in this case to draw the hybrid. And all I'm doing is I'm taking an average of the bond orders and the charges. 3 plus 2 is 5. 5 divided by 2 is 2.5. 1 plus 2 is 3. 3 divided by the two structures is 1.5. Minus 1 plus 0 is minus 1. Divided by 2 is minus a half. Plus 1 is plus 2. Divided by 2 is plus 1. Negative 1 plus negative 2 is negative 3. Negative 3 divided by the two structures is negative 1.5. That's my hybrid. Okay, comment on its suitability. And what it's asking you to do is to invoke the fourth factor, which is the distribution of charge. In other words, now that I've built the hybrid based upon the two most stable structures, is that really the best looking hybrid? Is that really a good representation of what the species should look like? And here's what I'm going to do. I'm going to ask, okay, fine. In my hybrid, I have more of the negative charge on the carbon than I do on the O. That doesn't seem to make any sense, because of the two atoms, O is much more electronegative than carbon. That is the same argument as saying, well, look, if I look at these two resonance forms, which one of these should make a greater contribution? Because based upon these three factors, they're equivalent. What I know O is a lot more electronegative than carbon. So why the heck would I have a resonance form that has a 2 minus charge on the carbon, and for heaven's sake, nothing, no charge on the O? That doesn't feed right. The more likely structure is going to be the one in which there is at least a negative charge on the O. So the O helps to share some of the burden. The carbon is stuck, right, having some negative charge, but at least it's not 2 minus. So I have a niggling feeling that of the two structures, 3 is really more stable than 4. So if I were to rank them in terms of stability, I would say 3 is up here, 4 is a close second, and then way below are 2 and 1. But the hybrid doesn't take that into account. The hybrid just assumes that these were 50-50. That's why we're averaging them. And in all reality, a hybrid must be a weighted average, understanding that one may be preferable over the other. So my comment, when it says the comment on the stability is, you know what, this is a good first approximation. But in reality, it looks more like this than it does like that. Right? So maybe in reality then, the charge on this O is closer to -1. The charge on this is closer to -1. There is more of a triple bond here, and there's less of a double bond here. So that's my comment. The comment would be, this is a good first approximation, but in reality, this would be closer to single bond character rather than double bond. The charge on this would be closer to -1. Wouldn't be -1 because there is contribution from this. It's closer to -1, the charge on this is closer to -1. So that's the comment. And again, sometimes the comment might be, this is spot on. Right? But sometimes the comment is, it's a good first approximation, but in reality it's closer to this structure than to that structure. Okay, I want to make one other point before we move on. This business of moving electrons and drawing the resonance arrows needs to be talked about a little bit. And you would have met this surely in Gen Chem 1. And I talked about this in class the other day when someone describes their boyfriend as a cross between Indiana Jones and James Bond. So I'm describing a real person in terms of species that don't exist, in terms of persons that don't exist. Or people say that a rhinoceros is a cross between a dragon and a unicorn. I'm not sure I see that, but okay. But I can describe a real animal, a rhinoceros, in terms of two things that don't exist. None of these structures is real. The true structure looks something like this, right? Now, cyanate is a real species. I can go to the store and buy cyanate. But when I do these arrows, I am not saying that these electrons move from here to